Okay, so hopefully you are seeing a picture of a flower. Is that the case?
Yes.
Okay, good. So yeah, I'm going to be talking about what's called the multi-crossing number for knots and the petal number for knots, literally taking a knot diagram and turning it into a flower. And it'll become clear what I mean as we go along. But let me just start with a little bit of background. So here you see the beginning of the table of knots. And this is the way normally we draw knots. Namely, we have places where we see a knot crossing itself. It's called a crossing, what I'm later going to be calling double crossings. And so this is the standard way that we draw pictures of knots. Shortly, we'll move away from that, but let me give a little more knot theory background. Kurt Reidemeister came up with a set of moves that allow you to get from any one diagram of a knot to any other diagram of a knot, a German mathematician. And these are called the Reidemeister moves. And I know that any of the knot theory experts in the audience know this very well, but for people who haven't seen this before, I wanted to give a little bit of background where if you have a diagram of a knot, you can do a move called a type 1 move where you put a little twist in like this. And that's not going to change the knot you have, it just changes the diagram. Similarly, we have a type 2 move where you take 2 strands of a knot and slide one past the other. And you have a type 3 move where you have a strand potentially behind a crossing and you push it past the crossing. And that would be a type 3 move. And it turns out that you can get from any one diagram of a knot to any other by a sequence of these Reidemeister moves. So here we see a picture of the figure 8 knot, this knot right here. And here we see a picture of the figure 8 knot with all of the crossings reversed from the original one. And it turns out that those 2 diagrams are equivalent, and you can see the sequence of Reidemeister moves, doing multiple Reidemeister moves at each stage to get from one to the other. And so this theorem that Reidemeister proved says 2 projections represent the same knot if and only if they're related through a sequence of Reidemeister moves. So I have a diagram, I start with a knot here, and another diagram over here. If those 2 are the same knot, there has to be a sequence of Reidemeister moves, 1, 2, 3, 2, 1, 1, whatever, to get from one to the other. And if they are not the same diagram, there is no sequence of Reidemeister moves to get from one to the other. And this is a fundamental idea in knot theory that we're going to use just shortly. Now, I want to tell you about another idea from knot theory that is very useful and we'll use shortly, which says if you start with a diagram of a knot, by changing the crossings, you can turn any projection of a knot into the trivial knot. So here we see a particular knot here, the 818 knot. I can get on this knot and I can change the crossings and turn it into the trivial knot. So for example, in this picture, here's how I'm going to do it. I'm going to start at a point on the knot. I'm going to start traveling along. And each time I hit a crossing, the first time I'm going to make that an overcrossing. And the second time I hit it, I don't change it. So this is the second time I hit this crossing, so it's an undercrossing, but this is the first time I hit this one overcrossing. So as I travel along, the first time I hit a crossing, I make it an overcrossing until I go all the way around to the bottom. Now this is the top view of that picture. Now I'm going to turn it a little bit to the side, and you'll notice what happens from the side view is I'm always going down, 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 down until I get to the bottom. And then I'm going to assume I have a straight stick back to the top. So from the top view, I can always see myself going downhill, around and around downhill till I get to the bottom, and then I go back to the top. So in fact, that is the same as the trivial knot. So that says this is a very sort of picturesque way of proving the fact that any knot, if you change the crossings, you can turn it into the trivial knot. And we'll use that just shortly. Okay, the beginning of this talk actually dates from a paper that appeared on the archive called Triple Crossing Numbers of Graphs by Tanaka and Teragato. And interestingly enough, this paper, as far as I know, has never appeared in print. And it appeared on the archive maybe 10 years ago now, probably something like that. And this paper was interested in trying to depict graphs in as simple a picture as possible. So here you see what's called the Peterson graph. This is a particular graph, and it's not a planar graph. You cannot draw this picture without having crossings of the edges. And if you try to draw it with crossings, you'll find that it's forced to have 2 places where the graph crosses itself, one here and one here. Now, what the authors of this paper were trying to do was come up with a simpler way to represent those. And they noticed the fact that you could actually take this edge here and pull it around the backside and around over to here to get just a single place where you have a crossing, only now it's a triple crossing instead of a double crossing. And the only reason I ever saw this paper was I was teaching a course on graph theory, and I was looking for interesting papers on graph theory for my students to read, and I stumbled across this paper, and I thought, well, wait a minute, if you can do this for graphs, why can't you do it for knots? And so that's really what got me started on the topic. And so we're going to call a triple crossing, which I'm going to denote like this. So this is a place where the knot crosses itself with 3 strands crossing. That's a triple crossing. T stands for top, M stands for middle, and B stands for bottom. So if I slide the top crossing off a little bit, this is in fact what my picture looks like locally. Okay, so what I've really done is concentrated 3 normal crossings, what we usually call crossings, but now we're going to call double crossings, into a single triple crossing. Okay, so if I have a projection of a knot with only triple crossings, I'm going to call that a triple crossing projection. So let me give you an example. These are 2 of the simplest knots, the trefoil knot and the figure-8 knot, and I'm going to get their triple crossing projections. For the trefoil knot, I have 2 triple crossings with labelings MTB and MTB, both MTB. And I have the exact same projection for the figure-8 knot, only now you'll notice the top labels have been switched to MBT instead of MTB, although the bottom label is the same. Okay, so both of these knots have a triple crossing projection with 2 triple crossings, just the crossings are a little bit different. So the question you want to ask, the first question you want to ask is it true that every knot has a triple crossing projection? Can every knot be represented by projections that only have triple crossings? And so, for example, this is an example that stumped me for a while trying to find a triple crossing projection of this particular knot. And the trick I'm going to use is I'm going to look for collections of what I call crossing covering circles. So here you see 3 diagrams of knots, and I'm going to show you my crossing covering circles. So these are collections of circles that pass through the crossings such that they're disjoint and they cross all of the crossings. So I've got 3 of these crossing covering circles in this diagram. I've got 2 that cover all the crossings in this diagram, and I've got 3 that cover all the crossings in this diagram. So that's a collection of what we call crossing covering circles. Okay, and I'd love to know that every knot projection has a collection of crossing covering circles like that. So that's kind of the question. And why do I care? Well, if it turns out that we have a collection of crossing covering circles, I can turn my double crossing projection into a triple crossing projection. And the way I do it is as follows. So here's one of those crossing covering circles. Notice it always has to pass right through a crossing. So it has 2 strands coming out to one side, 2 strands coming out to the other. I'm going to take one of the crossings and I'm going to take the over strand on that crossing. And instead of having it pass straight across the circle, I'm going to wrap it around the circle and then cross over the circle as I have in the second picture here. Notice this was an over crossing here. So when I do that, I'm going to pull it over everything in the diagram before I come around to here. What have I done? I've turned 3 double crossings into 2 triple crossings, and I lose the original double crossing. It's gone. Okay, I'm going to call that a folding. Okay, so I claim that every knot has a triple crossing projection, and I'm going to prove that for you in a second. But if that's true, then in fact we can define the triple crossing number of a knot, which I'll call C sub 3 of k, to be the least number of triple crossings in any triple crossing projection of the knot. Now, in the case of these 2 knots, you cannot get a single triple crossing projection, a projection with a single triple crossing. So that tells us that the triple crossing number of the trefoil knot is 2, and the triple crossing knot of the figure-8 knot is 2. All right, so now I want to prove this fact. Every knot has a triple crossing projection. Here's how I'm going to do it. First, I'm going to show that every projection has a crossing covering collection of circles, okay? Once, if I can prove that, then I'll be able to use these foldings, okay? Now, how am I going to prove that every projection has a crossing covering collection of circles? We'll start with any projection, and you'll remember we already proved you can turn any projection into the trivial projection by changing crossings. So that's the first thing I'm going to do is take my original projection, I'm going to turn it into the trivial projection by changing crossings. Notice changing crossings does not affect whether or not you have a collection of crossing covering circles. That's completely independent of how each of the crossings is set. So I still have a projection, happens to be a projection of the trivial knot, that I want to find a crossing covering collection for it. But I know that if I have a trivial projection, I can turn it in, if I have a projection of the trivial knot, I can turn it into a trivial projection, just a circle, by Reidemeister moves, because I know Reidemeister moves can turn any projection of a knot into any other projection of a knot, okay? So that means that if I have an original projection by changing crossings, I can turn it into the trivial projection, and then by a sequence of Reidemeister moves, I can turn that into just the trivial projection with just a circle, okay? So that means if I can show that that trivial projection is a crossing covering collection, then it's enough to show that Reidemeister moves preserve the existence of a crossing covering collection of circles. So I'm going to look at what the Reidemeister moves do to a crossing covering collection of circles. And I want you to picture as if I'm starting with the trivial projection that needs no crossing covering circles, okay? So I can start with no crossing covering circles if I want. And now I'm going to build up a more complicated projection. Well, if I put in a type 1 move, I'll add one crossing covering circle that will cover that circle, okay? So now I still have a crossing covering collection. So if I started with a crossing covering collection, I still have a crossing covering collection. Also, there's a type 1 move where you remove a little crossing like this. And if I had a crossing covering circle that passed through that crossing, I'll leave that crossing covering circle. So a type 1 move does not impact whether or not you have a crossing covering collection. If I do a type 2 move, then I can just add a crossing covering circle to cover the two new crossings. If I do a type 2 move where there was a crossing covering circle through there already, that covering crossing circle will deal with the two crossings here. If I undo a type 2 move and I had two crossing covering circles covering those crossings, then I will just serger my crossing covering circles and I'll still have a collection of crossing covering circles. So we're just proving that type 1, 2, and 3 moves do not change the fact that you have a crossing covering collection. I could even have 3 crossing covering circles passing through the center where I want to do a type 2 move. First, I would do surgery on them, and then I would do my move. And then finally, I could have an even number of crossing covering circles passing through the center. First, I would do surgery on them, and then I would do my move. But in all cases, if I started with a crossing covering collection, I still have a covering crossing collection. Finally, let's look at type 3 moves. If I have a crossing covering circle like this, it's preserved when I do that type 3 move. If I have 3 crossing covering circles crossing each of my crossings in my type 3 move, I can do surgery on them and add a component in here. This is still a valid covering crossing, it's very hard to say this, covering crossing circle collection. And then I do my move and I still have a crossing covering circle collection, okay? And then finally, the last case is if I have a type 3 move where I have a crossing covering circle crossing 2 crossings and 1 here, then I can do my type 3 move and I still have a collection, okay? So the end result is that the type 1, 2, and 3 Reidemeister moves preserve the fact I have a crossing covering collection. If I start with the trivial projection, it has a crossing covering collection of circles, namely the empty set. And then I do my moves to get the very complicated projection I'm interested in. And the moves preserve the fact there's a covering crossing collection. So that new projection also has a covering crossing collection. And then I can change my crossings back. And that does not impact the fact that I have a crossing covering collection of circles. Okay. So in particular, let me go back to that for just 1 second. So in particular then, taking that collection of circles, I can fold along them and I get a projection that only contains triple crossings. And in particular, I just want to notice a corollary, which is because I lose a crossing every time I do one of those foldings, that means that the triple crossing number of any knot will be less than or equal to its crossing number minus 1. Okay, good. What about higher order multi-crossing? So that's triple crossing number and the triple crossings and triple crossing number. What if I had n strands passing straight through a crossing? So instead of having 3, I might have 4, as you see in this picture right here. Well, there's an easy trick to turn any standard projection into a quadruple crossing projection. Namely, I'll take this understrand and I'll just go back and forth a couple of times, and then you'll see right here at the center a quadruple crossing. And so that allows me much more easily than in the triple crossing case, but in the quadruple crossing case, that is an immediate proof that every knot has a quadruple crossing projection, and therefore the quadruple crossing number is well defined. So that's C sub 4 of K is the minimal quadruple crossing number for any knot. Okay, so now we have a double crossing number, which is the traditional crossing number, a triple crossing number, and a quadruple crossing number. Okay, but now there's a lot more of quadruple crossings. Namely, there are 6 different quadruple crossings. 1 represents the top strand in my crossing, 2 represents the second highest strand, 3 represents the third highest strand, and 4 represents the fourth. If I start with my top strand, then any permutation on 2, 3, and 4 is a possible quadruple crossing, which is why I get 6 different quadruple crossings. Those numbers go up quite fast. What if I want to turn a regular projection into an n crossing projection? Well, if n is even, I'm going to do the analogous trick that we did for quadruple crossings. Namely, I'll just go back and forth a few more times, and that makes it easy to see that you always have an even crossing diagram. If n is odd, first I'll turn my standard diagram into a triple crossing diagram, and then I'll use this trick on it. And it will allow me to get from a triple crossing to a quintuple crossing or a septuple crossing, etc. So those 2 tricks allow us to show that for any n, every diagram has an n, every knot has an n crossing diagram, and therefore an n crossing number. Okay, so we've just proved this fact. So let's take a look at some examples. We saw the trefoil knot before. We know that its double crossing number is 3. We saw that its triple crossing number is 2. And in fact, its quadruple crossing number is 1. Okay, so you can actually get a projection with just a single, what I call a multi-crossing at the center. And so this is the quadruple crossing number for, in fact, the trefoil knot. Now, this is work that I did with undergraduates. So here we see the group of undergraduates right here. All of these students went to graduate school, and these are the graduate schools they went to. So Ursula went to Duke, Jesse went to MIT, Daniel went to Michigan, Samantha went to Georgia Tech, Daniel went to Princeton, Ashley went to Brown, and Scott went to Stanford. And they're all right at the point of finishing their PhDs right now. Very strong group of students. This is our summer program called the Small Program, funded by the National Science Foundation, and we get phenomenal students for this program. And so here is the table of values that we found for the various multi-crossing numbers for knots. And I realize you might not be able to see that well, but at the top here we see the trefoil knot. So here's the trefoil knot. We saw its multi-crossing numbers 3, 2, 1, and then it stays at 1 from then on. This is the figure 8, 4, 2, 2, 1 going down, the 5, 1 knot, the 5, 2 knot, the 6, 1 knot. Here are some composite knots, and this table goes through all 9 crossing knots. Now you'll notice there's still plenty of holes in this table. For instance, we don't even know the triple crossing number of 7, 1, which is the 2 braid knot. Where it's embarrassing that we don't know that number, but in fact we do not. There's also some other holes like that in various places. So a lot of these numbers we don't know. These symbols here represent the ways we found these numbers. A lot of this was heavy duty computer work. Okay, so we put in various diagrams and get the computer to find out the simplest diagram that it can. So lots of this involved computer work, and there's great opportunities here, tons of open questions in terms of these numbers. Here's just a close-up of that top part of the diagram. And you'll notice that one of the things people ask is, well, is this a complete invariant? In other words, can you distinguish all knots simply by their multi-crossing number? And sadly, the answer is no. You'll notice the 6, 2, 6, 3, and the composition of 2 trefoils all have the same sequence of multi-crossing numbers. You might also wonder, is it true that once it goes down to 1, it stays at 1? And the answer is we do not know that. Okay, what we know is once it gets down to 1, conceivably the next number could be 2, and then it'll stay down at 1 from then on. But we cannot prove that that does or does not happen. We've never seen an example where that happens, but we do not have a proof that once it gets down to 1, it has to stay at 1. So lots of interesting questions about these values of multi-crossing numbers. But here's a fundamental question. You'll notice I showed you that picture of the trefoil knot with just a single multi-crossing. does every knot have a projection with a single end crossing for some n greater than or equal to 4? And that asks the same question as, does the multi-crossing number always have to go down to 1? Okay, that's an equivalent question. And we're going to define a diagram like this that has a single multi-crossing. We call that an Uber crossing projection. So that's a projection with a single end crossing. And this is a good example because you'll see that these loops that come out of the crossing can be nested, where you have one loop inside of the others. But in particular, a very nice Uber crossing diagram is one that looks like this, what we call a petal projection. Okay, and so a petal projection has a single multi-crossing at the center, and then it has a bunch of loops coming out, and none of them are nested. Okay, so it's a very special example. All of the strands have to go straight through, and we number the strands with the height at which they're going through that central crossing. So 1 is always the highest one, the top one. So it goes through 1, and then 2 would be the second level, etc. And then you can keep track of these very easily. You can either keep track of them by following the knot around, in which case I get a permutation 1, 3, 6, or you can just read it around the boundary. It's the same, 1, 3, 6, 9, 5, and you just have a permutation that represents that knot, okay? So this is another small group from the previous year, and I should mention that one of these people was a postdoc, Seo-Jung Park from KAIST, okay? So, and she came for the summer to work with us, and she was great. And these students also all went to graduate school. These are the graduate schools that they went to, a variety of good schools, and they are also either finished their PhDs or just on the verge of finishing their PhDs. Another great group of students, one of whom is not in the picture. Tom Crawford is not in the picture. And they and I proved that every knot has a petal projection. Okay, so it turns out that every single knot can be represented by a petal diagram, and therefore a minimal petal number. So the petal number of a knot will be the least number of loops in a petal projection of K. So I want to look at an example, and I'm actually going to, rather than show you these pictures, I'm actually going to stop sharing and show it to you live because I think it's more fun live. So I'm going to show you, I'll use this example right here. So here is a 3D printed knot, and it looks quite ugly, okay? Until you turn it just right, and if you turn it just right, you see that in fact it is a petal projection. Okay, it has a petal projection. Okay, and I have one more example of that, so I don't know if it makes any difference, but I'll show you another one. So here's another one. Looks awful, looks terrible until you turn it just right, and then you see that it has a petal projection like that. Okay, every knot can be put into a form like this. Okay, so every knot has a representation like this, and it has a petal projection with a minimal number of petals. So that turns out to be a very useful fact. Okay, so that was the side view, that was the front view, which I just showed you live. Okay, so I want to prove this fact. I want to prove to you that every knot has a petal projection, so I'm going to prove it, and the proof is going to be by an algorithm. Namely, it's just an algorithm that will turn any knot projection into a petal projection, and we're going to do a very simple case because otherwise the algorithm gets messy, but it works in all cases. So we're going to start with the trefoil knot. Step 1, I'm going to move the projection around so that all the crossings occur on a single vertical line, which you see dotted right here. So I've just shifted things around a little bit in the diagram. So all of the crossings are right on this vertical line right here. Then I am going to get on the knot on the rightmost point. I'm going to travel along it, and each time I hit a crossing, the first time with an over, I'll put an O on it for over, and the first time I hit a crossing with a U on it, I'll put a U on it for under. And I'll travel around until I've hit all the crossings at least once. Okay, so every crossing will get an O if the first time I hit it is over, and a U if the first time I hit it is under. I'm going to slightly move the crossings with an O to the right and the crossings with the U to the left. Okay, so I'm just going to move things over a little bit, each of those. The next thing I'm going to do is I'm going to rectilinearize the picture. Namely, I'm going to turn it into vertical line segments and horizontal line segments that mimic the things that I see in this picture. Okay, so I haven't changed anything other than just straightened it out so it looks like this. The next step is I'm going to get rid of any sticks I don't need. So you'll notice here I have an extra stick going down that I don't really need, so I'm just going to clean it up a little bit until I get to a diagram like this. okay? The next step is I'm going to take my diagram starting at my initial point, and I'm just going to move things in three-dimensional space a little bit. Right now I was thinking of my diagram as lying in the plane, so think of that as the XZ plane. And what I'm going to do is, as I move around my diagram starting from this point here, each time I get to the first stick here is right along, think of it as the y-axis. Then I come down, and this used to be in the plane, and I'm just going to twist this horizontal stick out of the plane a little bit in the counterclockwise direction, okay? So I'm just going to shift it a little bit. Then I'm going to go, whoops, sorry, then I'm going to go to the next stick. So that was the first stick, I shift a little bit, and the next horizontal stick, I'll shift it a little bit more. Now, of course, that's going to make the vertical stick slant a little bit. I don't care about that, that's fine, but I'm going to shift that a little more, and I'm going to go to my next horizontal stick, shift it a little bit more. So each stick gets turned counterclockwise, the first one a little bit, the next one a little more, the next one a little more, until I get back to my starting point. Now, the view from above looks like this. So my first stick was here, then the next stick got shifted over a little bit, then over a little bit. So this is the view from above. And then there was the last stick where I got back to the other one, which is outside. Now you'll notice this diagram is not a petal diagram, but it's pretty close to a petal diagram. Looks like this, okay? And these are the labels on the sticks. So the one stick, the two stick, the three stick, the four stick. So, and it's always going to be the case that there's just one outer loop that ruins it from being a petal diagram. And so what I'm going to do is fix it. So this is what we call a pre-petal diagram. And I'm going to take that outer loop and I'm just going to pull it inside like this. I'm going to pull it down, and then I get, in fact, a petal diagram. So from the diagram I had before, one little move like that turns it into, in fact, a petal diagram, okay? So now you can start calculating the petal numbers for lots of different knots. And so here we see some examples of the petal numbers that we did. A lot of this was done again by computers, by that same group of undergraduates that I showed you before. And so these are the petal numbers for the knots, and these are the permutations that correspond to the particular knots that you see there, okay? So you can calculate a lot of these numbers. So we did it again through the 9 crossing knots. I tend to stop after 9 crossings. This idea of petal numbers turned out to be very useful. And so, in fact, some authors, Haim Even Zohar, Joel Haas, Nati Lineal, and Tal Noack have written 2 papers about petal numbers, and they're using them to generate random knots. So it's kind of an interesting way to generate random knots. And so these are 2 papers that they wrote about it. And the idea is very simple. As I said, when you're representing a knot using its petal diagram, you're just representing a knot by a permutation on what turns out to be an odd number of integers, okay? So we just take the integers from 1 to n, an odd number of integers, and we take a permutation on it. And each permutation represents a knot. And so therefore, if you want to generate random knots, you just generate random permutations, and that will generate random knots. And so that's what they do, generate random knots of length n to generate random knots with petal permutations of n petals. And then what they study is they study the invariance of those knots. They try to figure out how knots will behave relative to this particular measure of randomness. Now, I want to talk just a little bit about virtual knots. I won't talk too long because I realize this shouldn't be that long. So let me talk about multi-crossings and virtual knots. So let me give you a little bit. This is joint work with students, Haim Even Zohar, who was in that last slide, who is not a student. He is a professor in Israel. And then the rest of these students were actually students of mine from Williams College. And many of you may know about Lou Kaufman's invention of virtual knots. And so virtual, this is one of my favorite pictures of Lou. Virtual knots are knots that have classical crossings, like the ones that we've been talking about so far, and then these special crossings called virtual crossings that you have to imagine aren't there. You should think about virtual knots are to classical knots the way imaginary numbers are to real numbers. They're an extension that allows you to do things that you couldn't do with just classical knots that turn out to be very useful. And just like we had Reidemeister moves for the classical knots, which you see over here, we have Reidemeister moves for virtual knots. So you can get rid of a single virtual crossing, you can get rid of 2 virtual crossings, or go back and forth like this. So we have a type 1, type 2, and a type 3 virtual Reidemeister moves. And then there's this mixed move that allows you to take two virtual crossings and push a strand through two virtual crossings over a classical crossing. There's also a move called the detour move, which actually follows from these other moves, that allows you to take anything that involves all virtual crossings and pass it over anything else like this. That's the detour move. Okay, so these virtual knots turn out to be very useful. So then you might ask the question, well, is there such a thing as a triple crossing diagram for virtual knots? Okay, do these ideas that I've been talking about extend? And incidentally, let me just say this. Whatever your favorite idea from classical knot theory is, you should ask, does it extend to virtual knots? And it turns out that lots and lots and lots of ideas have been extended, but there's still lots of other ideas. Right now, I have a group of students working on extending what's called hyperbolic knots to virtual knots. It turns out a lot of those ideas extend. So there's lots of interesting questions about this. It turns out that you can extend the idea of triple crossings to virtual knots. You can have three different types of virtual triple crossings. So you can have what would be a classical triple crossing, a virtual triple crossing with two virtual double crossings in it, which I would represent like this, and a virtual triple crossing with three virtual crossings in it. Interestingly enough, you cannot have a virtual triple crossing with one virtual crossing in it. So you couldn't have just one of these two here and two classical crossings. And the reason is that if you did, it would allow what's known in virtual knot theory as a forbidden move, and you cannot allow forbidden moves. So that's the reason that never occurs. But you can have these three types, and it turns out that you can actually prove that every virtual knot has a virtual triple crossing diagram. So you can do all of the theory that we've been talking about for virtual knots, just like you can do them for classical knots. Finally, what about petal projections? Do they extend to virtual knots? So this pretty idea of turning a knot into a flower, can you do that with virtual knots? And it turns out that the answer, in fact, is yes. So it turns out that you can use what's known as the Gauss code, which is a code for representing a diagram for a knot. And the Gauss code works for classical knots and it works for virtual knots. And you can show, using the Gauss code, you can show that you can turn any virtual knot into a virtual triple crossing diagram. Here is sort of an exploded version of a virtual petal diagram, rather, I think I said that wrong, petal diagram that you construct from this particular Gauss code. Because it's made from that Gauss code, that means the knot that results is the virtual knot that had that Gauss code, and you can construct it in a way like this. So any of the questions that you can ask about petal knots, petal number for knots, you can also ask in the category of virtual knots. Okay, so I think I am going to stop there and open it up for questions. But thank you everyone for listening, and I would love to have any questions that anybody has. I have tons of other material I could have talked about, but I really wanted to keep this appropriate for anybody who's getting started in knot theory, but certainly if anybody has any other questions that are more advanced, I'm happy to answer those as well. And I will stop sharing so that people can ask questions.